Hello, I welcome you all to this another interesting screencast. We are going to be solving this engineering mechanics problem, and it reads the semi-cylinder of mass m and radius r lies on the rough inclined plane for which phi is equal to 10 degrees, and the coefficient of static friction is equal to mu s equal to 0.3. Determine if the semi-cylinder slides down the plane, and if not, find the angle of tip theta of its base AB. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So we've got a semi-cylinder of mass m, and it has a radius r, and it is lying on a rough inclined plane. So this simply means there is friction between the cylinder and this contacting point with the inclined rough surface. We've been told that the cylinder has a weight W. Okay, so we expect the weight to act like that, right? It's acting through the center of gravity. So they've told us is mass m, so we'll convert it to the weight, and we know it's going to be mg, and g is equal to 9.81 meters per second squared. So just write it as 9.81 m for mass. Okay, mg. All right. What else do we have? Of course, this is a rough surface. So imagine we've removed the surface. We just want to indicate the forces or the reaction forces on the semi-cylinder at the point where it is in contact with the inclined rough plane. So that is what we want to indicate, assuming we have removed this surface. So we expect, because this cylinder will have a tendency to move in this direction like this, and to counter this movement we expect some friction force here that we are going to call F, right? Okay, and with a friction force there is always this normal force. This is a normal force at the point or at the tangent to where the cylinder is in contact with the with the inclined surface. So we have a normal force. This normal force is coming from the inclined plane. Is it well drawn? Okay. All right. So we know about this to say when we have, let me draw it properly, because we know according to the rules of a semicircle, we expect this particular normal force to go through the center of the circle, right? So that it makes a 90 degrees with this particular surface like this. This is what I want to achieve. Okay, right? You know about this, right? Right. Moreover, then the reflection force is always perpendicular to the normal force. But the point I just wanted to stress is it will go through this point here, the center of this semi-circle, okay? This point O, all right? Point O, center of a circle, but this is a semicircle. So that center of the circle, we're calling it O, but we only have a semicircle. So this is our N, right? So a few other things that we need. we are going to use a reference. See, instead of we're going to use a reference like this one. We have x, y. Okay, so because we are going to use this reference, the weight, okay, of the semi-cylinder is in the right coordinate system, so we need to convert the friction force F and the normal force. So to do so, we expect a reaction from F. I mean, we expect the components from F, one like this and another one like this, right? So these are components of F. All right, so this is phi there. So this one here is going to be equal to F cos phi. This one will be, maybe this is too long, right? Maybe I bring it here. This one will be F sine phi. Okay, and since this angle here is also phi, we expect components also of the normal force in our coordinate system, right? So we expect one like this and another one like this, right? These are components of the normal force. Okay, so this one is going to be equal to n cos phi, right? And this one will be n sine phi. All right, I think for now this is enough, but we'll come and add additional information when we apply the summation of moments about all. For now, let's leave it like this. We'll come and add more details later on. So now let's count a number of unknowns. How many unknowns do we have? We have F, which is the friction force. We have the normal force N, and we have theta. All right, so we have three unknowns. This semi-cylinder has dimensions, which makes it easier for us to take moments. So we have altogether three equations of equilibrium, which makes it good because we are able to solve all these unknowns with their variable equations of equilibrium. But after I've done the solving, we need to come and check because they've asked us here to find out whether the semi-cylinder will slide down the plane or not. So we need to check. All right. So once we are done with solving, we'll get back to come and do what? Check. Let's apply the equations of equilibrium quickly. So we have summation of forces in the x direction, and this is what we have. What do we have? We have F cos phi, this is positive, minus n sine phi equal to 0. Given that phi is equal to 10 degrees, okay, therefore F, can you write F equal to n tan 10 degrees. Is that fine? We can write it like that. Then we have summation of forces in the y equal to 0. Okay. What do we have? We have minus 9.81 m plus n cos phi plus f sine phi, okay, equal to 0. All right. So what we are going to do, okay, what do we need to do now? We can write this also. Maybe we can simplify it further. We can say, let's replace this here Okay, if we replace that there and then make n subject to the formula in normal force, our n will be equal to 9.81 m divided by cos 10 degrees plus tan 10 degrees times sine 10 degrees. Mind you, phi is equal to 10 degrees. So this is our n. So let's take another equation. Let's take another equation about point O. Summation of forces about that point. Summation of forces about that point equal to 0, and clockwise being our reference. What do we have? So before we take moments, I'll need to draw to indicate other components that are here. So this is going to have components. We know that this angle here is phi. Therefore, this one here is going to be phi, right? I mean theta, sorry. Theta, sorry. Therefore, we are going to have a component here, okay? And then we have another component there. We need these components as we take moments, okay? So one component is going through. So this one here is 9.81 m cos theta, right? And then this one is 9.81 m sine theta. All right, so let's take moments about point O. Okay, the one going through point O and normal force will not have an effect. We'll only consider one. All right, let's do so. So F is going to cause a counterclockwise moment. F by R, the distance to point O is R, the radius. F times R, the lever arm, and clockwise positive. Then minus 9.81 m sine theta times the lever arm, okay, which is 4r. Okay, this is the location of our center of gravity. 4r 3 pi, okay, equal to 0. All right, so F, we already know what it is. Okay, we said F is equal to n tan 10 degrees, and our n, we also said our n is equal to, let's calculate what n is from this equation here. All right, so we have 9.81. Okay, first cos 10 degrees plus tan 10 times sine 10, then 9.81 divided by answer. So we have n equal to 9.66096. I just want to make it a little bit longer so that I don't lose the accuracy m. All right, and therefore our F is going to be equal to, if we replaced this here, okay, so this becomes times tan 10 degrees. This becomes a 1 point. This becomes a 1.70349 m. All right, so therefore replacing this value here, this F here, okay, replacing that value there and making sine subject to the formula, then we'll have sine theta is equal to F, which is 1.70349 m divided by 9.81 m times 4 divided by 3 pi. Therefore, theta will be equal to, what is our theta equal to? Let's see. So we have 9.81. Of course, the m, the mass, cancels out. So 9.81 times 4 divided by 3 pi. Okay, then we have 1.70349 divided by answer. This is not 9.81 times 4 divided by 3 pi. Okay, 3 pi. Okay, then we have 1.70349 divided by answer. Okay, then sine inverse of answer, we have a 24.15 degrees. Great. So found the angle, but we found this angle of angle theta. So we need to find the other part of the question, whether the semi-cylinder will slide down or not. So we need to find the maximum friction. So the maximum friction is mu n, and we know our mu is 0.3. Okay, this is the maximum friction that we need to compare with our friction F. So mu n times n. What is our n? Our n is 9.66096 m. So if we multiply that, 9.66096 times 0.3, this gives us a 2.898 m. Alright, so therefore our F, okay, the friction at that point is equal to 1.703 m, okay, is less than mu n, which is the maximum friction, which is equal to 2.898 m. Therefore, no slip will take place. Okay, no slip will take place, or the semi-cylinder will not slide down. Okay, so I think this is about it. We found the angle. We also found the result that the cylinder won't slip down. Alright, I think this is about it. This is really about it, and I hope the video was helpful. And if it was, give me a thumbs up, like my video, and continue subscribing and sharing my channel. Bye bye, and see you in my next screencast.